Good day and welcome back to the beginning of our discussion on maximum and minimum values. So up to now, we've spent a great deal of time introducing the concept of differentiation and various properties of differentiation related to functions of several variables. And we are now ready to move on to a very important application, the idea of optimization. That is, given a function of two variables, are there various methods and techniques we can use to determine where maximum and minimum values will occur? But before diving into those associated techniques, the first thing we need to do is make sure that we are all on the same page when it comes to language of what it means to be local maximums, local minimums, and so on. In this first video, we'll develop some of the terminology related to local maximums and minimums, make sure we are all on the same page, and then we'll begin discussing certain characteristics that we would expect to find at these extreme types of values. Then in future videos, we'll go through the procedures for finding and classifying extreme values. So to begin, the idea of maximums and minimum values are hopefully very intuitive. If we want to know what does it mean to say a function of two variables has a local maximum at a point, that essentially is just saying in words, at AB, you are bigger than everything around it. So physically, you're at the top of a little hill. In terms of symbols, we would say that we have a local maximum at AB if that function value at AB is bigger than the function values for points surrounding AB. And how we will write this is just say for x, y, our inputs, close to AB. And depending upon the application, we may only be interested in that output, f of AB, and f of AB is called the local maximum value. And that word value is really indicating that we're talking about an output of a function. So we have the local maximum at AB, i.e. where it occurs, and the local maximum value is the associated output. Similarly, we will have a local minimum at a point AB if you are smaller at AB than you are at surrounding points. That is to say, if f of AB is smaller than or equal to the function outputs at xy, where once again xy is close to AB. And the similar language is we once again refer to that output as being the local minimum value. Now, sometimes we're only interested in local maximums, local minimums. Other times we might want to know, say, an absolute maximum or an absolute minimum. So in terms of an absolute maximum, we would say if f of AB is bigger than f of xy for every single possible input in the domain of f, then AB is an absolute maximum of f. So that's where that absolute maximum occurs. And I've left some spaces here, but that's really just to insert the associated language for minimums without having to kind of rewrite everything. So similarly, if we had f of xy is always bigger than f of AB for every single xy in the domain of f, that would be telling us that the smallest possible output would be this f of AB. So then AB would correspond to an absolute minimum value. And we should be able to kind of graphically maybe notice when these will occur. And if we were to draw a simple picture, such as the following, which I've added in here, I'm thinking that this is representing the surface of some function of two variables. And notice, we can pick off where we have these peaks that would correspond to a local, maybe even an absolute maximum. And in these valleys, we would have the local minimums or possible absolute minimums. So we can see very clearly from a picture such as the one drawn here where those local maximums and local minimums might occur. Now the question becomes, though, what is a defining characteristic that occurs at those points? And let me give you kind of a quick reminder. when we were in this Calculus 1 scenario, and we wanted to find absolute maximums and minimum type values, or locals, what we noted is that you get these peak values occurring at a value C, and we identify those how? And thinking back to Calculus 1, we identified them by the fact that at one of these extreme values, the tangent line is horizontal. So if you were going to have one of these local maxes or local mins, in Calculus 1 we said that would imply the tangent line would be horizontal, i.e. the value of the derivative is equal to 0. And it turns out that we can kind of see the same exact thing happening in the case of functions of two variables. If we are at, say, this extreme value where we have a local maximum, if we were to draw the tangent plane at that point, it's going to be a horizontal tangent plane. Similarly, if we were to attempt to draw the tangent plane at that local minimum, it's also going to be a horizontal tangent plane. So very similar to our Calculus 1 experience, if a function of two variables has a local maximum or minimum at a point AB, above, the tangent plane is going to be horizontal at that point. And note, we should be able to use properties of calculus to determine when that occurs. In Calculus 1, it was simply when the derivative was equal to 0. Now in our case, when we write down the equation of the tangent plane, in order for it to be horizontal, we actually need two derivatives, in a sense, to be 0. What we would need to occur would be that the partial with respect to x at AB is 0, and the partial with respect to y at AB is equal to 0. And if both of those partials are equal to 0, this is telling us we have a horizontal tangent plane. And just to make sure we're all on the same page, why is the tangent plane horizontal? Well, let's kind of remind ourselves of that formula. It's always a good thing to go through a quick reminder. The tangent plane at AB is given by the following formula. We have z equals f of AB plus the partial with respect to x at AB times x minus a plus that corresponding y term. And if we know that the partials with respect to x at AB is 0 and the partial with respect to y at AB is 0, those two terms disappear, and what we are simply left with is z equals a value, and z equals some output value would be corresponding to the equation of a horizontal plane. So at this point, what we have observed is if we have a local max or minimum at AB, then the two first partials will be equal to 0. And the question is going to remain and hopefully be answered in our next video. If these two first partials are equal to 0, are we guaranteed to have a local max or min? So stay tuned and take care.